Welcome to the Fundamentals Lecture for Chem 118 Experiment 6. Now note carefully here that we have leapt over experiment number 5. This is the experiment that will follow Chem 118 Experiment 4. During Chem 118 Experiment 6, we're going to be investigating how to manipulate equilibria and reversible reactions to our will. In order to do this, we're going to discuss esterifications, acid hydrolysis, and saponification reactions, all which involve esters. We're also going to have a guest lecture from Professor Tyler Durden, who's going to give us a history lesson on one of these very important chemical reactions. But let's get straight to the point this week. Our inquiry this week is, how do we obtain the best possible yields from a reversible reaction? Are all reactions unidirectional, or do we have the ability to reverse them and dictate their direction based upon how we set them up in the labs? And when we do so, how do we ensure that we get the maximum yield of the desired product at the end of the process? By the end of this exercise, we'll have a better idea of how chemists go about designing reactions and syntheses that do just that. This week we'll be dealing with the Fischer Esterification, a very popular reaction which allows us to turn organic acids and alcohols into esters using a mineral acid catalyst. It's a great reaction to use. It's very, very popular, but it's also an equilibrium. So it doesn't run completely to a state in which only the product is present and all the starting material has been consumed. So why is it that this is such a popular way to convert these reagents into esters when we know from the beginning that it's never going to be completely done? We're going to answer this question about how we can maximize our yields from equilibria using a fairly simple Fischer esterification reaction shown here. This is the reaction of benzoic acid with methanol, again under acidic conditions, to create methyl benzoate and water. Now the equilibrium constant for this reaction is just about 4. Just like most Fischer esterifications, it's very close to 1, meaning that it's about a 50-50 equilibrium. It really doesn't favor one side much more strongly than the other. So with this in mind, if we were to mix 1 molar solutions of both starting materials and allow equilibrium to establish itself, how much product would we expect to form? Now we want to answer this question before we go into the lab and attempt to use this reaction in a synthesis so that we can save a lot of time, energy, and money. To quote Sun Tzu, "The general who wins the battle makes more calculations in his temple before that battle is fought, and the one who loses is the one who doesn't." Essentially, what Sun Tzu is saying here is, do your homework. Flip the envelope over and scribble down the calculation, and you may save yourself a tremendous amount of time and energy. Or you may be able to prove to yourself that success is very likely, and then decide to take action. So let's take Sun Tzu's advice and do some math before we go out there and try to run the reaction and convince ourselves it's possible to get a meaningful yield from it. Here's our reaction again. Benzoic acid and methanol reacting to form methyl benzoate and water. And remember, we were going to assume we have 1 molar of each starting material. Now, to determine the equilibrium conditions, we're going to have to use a tool from general chemistry, our old friend, the Rice table. So, let's get started. We start with 1 molar of each starting material, just as indicated. Now, if I mix these two and freeze time and don't allow the reaction to take place, at the very beginning of the reaction I have absolutely no product. Then of course the reaction will establish an equilibrium, which means the concentrations will change. And the reaction stoichiometry tells me that they will all change by the same quantity. Minus X for my reagents, plus X for my products. This allows me to calculate their equilibrium concentrations in terms of that variable X, making the equilibrium constant expression one equation with one unknown, and therefore a soluble equation. I simply use X for my numerator terms, because that's what my product values were, and 1 minus X as my denominator terms because that's the concentration of my starting materials once equilibrium is established. And if I solve this equation, I find that x is equal to 0.67, or about a 67% yield. Now this isn't terrible, but by organic synthesis standards, it's pretty disappointing. We'd rather get a much higher yield. So is there something we can do to increase the yield that we get from this process? Well, let's think a little bit more about this. It's an equilibrium process. And who do we know that gave us some very valuable tips on how we can manipulate equilibria? That's right, our old friend Le Chatelier. He's back again. In the case of this equilibrium, there are a few tricks we can try, including increasing the concentrations of various reagents or decreasing the concentrations of various products as the process takes place. And it turns out that in most Fischer esterifications, it's a relatively simple process. All we have to do is pick the cheapest reagent and crank its concentration sky high. By doing this, we'll affect the equilibrium in the way that we want to. Let's check that out. Here we are again on the back of the envelope, looking at our reaction, benzoic acid and methanol to form methyl benzoate and water. Making a few basic assumptions, such as volumes and densities are unchanging, and contributions from other species are negligible. Let's just assume the reaction takes place perfectly. What percentage of that acid do I expect to be esterified at equilibrium if, instead of using 1 molar methanol, I use pure methanol? Well, things have changed a little bit. I've still got my rice table, but this time my starting concentrations are drastically different. For example, let's say that I put 5 grams benzoic acid into enough methanol to make 0.025 liters of solution. Well, that gives me a 1.64 molar solution of benzoic acid, not much more concentrated than our hypothetical 1 molar example previously. But what about that methanol? Remember, we're going to assume that because there's so much methanol there that its concentration is essentially the same as pure methanol. So what's the concentration of methanol in methanol? It's actually easier than you might think to determine. We simply take the density and the molar mass of methanol and combine them so that the terms cancel to give us moles per liter. When we do this, we find that the methanol concentration in pure methanol is 24.7 molar. Huge number by comparison. So how's that going to affect our equilibrium numbers? Let's find out. Again, remember, we start with no product, and then our system moves to reach equilibrium. So at this point, our equilibrium concentrations can be easily calculated based on the stoichiometry, which in our case is all 1 to 1 to 1 to 1. Very simple. When I run these numbers, what I discover is that my result is 1.61 molar product. That is almost a quantitative conversion. It's 98% conversion. To which Sun Tzu says, 谢谢. And of course, Le Chatelier says, 不客气. Thank you and you're welcome. And forgive my terrible Chinese. So we've determined that we can use esterification reactions to create new products in the lab in very high yields as long as we're careful about our synthetic design. Why would we ever want to do that? Well, one reason that we might want to do that is esters make up a large amount of fragrance additives and flavor additives as well. Very small organic molecules with the ester functional group have very familiar fragrances and flavors. For example, ethyl pentanoate, which smells like apple. Isoamyl acetate, which has the characteristic aroma of bananas. And bornyl acetate, which creates quite a different aroma, that of pine. All of these esters can be synthesized cost-effectively from their corresponding alcohols and organic acids using a Fischer esterification. And it's because they're so easy to make from such inexpensive starting materials that we find them in use so frequently in these industries. But enough about how to put esters together. Remember, equilibria can be run in two different directions if we properly design a reaction system. And it turns out that there are actually lots of great reasons to take esters apart as well. And there are actually two different techniques available to us in the lab to do this that are very easy to run. The first is the acid-catalyzed hydrolysis, which gives us carboxylic acids and alcohols. Now, if you look at that top reaction, you may notice something. It's the exact reverse of the Fischer esterification reaction. So in order to manipulate this reaction, we can simply increase the concentration of water. So if we expose an ester to water with an acid catalyst, we can break it back down into its constituent alcohol and carboxylic acid, but of course never quantitatively. It turns out there's actually a much better way to do this, at least in most cases, and that's using hydrolysis under basic conditions, which allows us to form a carboxylate salt and an alcohol. I haven't shown you the mechanism for this reaction, but you should be able to work this one out for yourself. And when you do, what you'll realize is that the final step of the process is irreversible, which means that as long as we have enough base present, we can 100% quantitatively hydrolyze an ester to form the carboxylate salt and alcohol. This is one of the reasons why the hydrolysis under basic conditions of an ester, or saponification, is one of the earliest known chemical reactions used by society. Shown here are two commonly available fats that are obtained from natural sources. Now, what we commonly refer to as a fat, or what we think of as being a solid, and in that case we'd be looking at something like tristerin, which is made up of a glycerol molecule condensed to form an ester with 3 different carboxylic acids which are saturated. Notice that there is a glycerol portion here which is chemically attached through an ester bond to 3 fatty acids. The same is true of oils, which are just liquid triglycerides, as is the example down here of a triolein, which again has a glycerol molecule condensed with 3 different carboxylic acids, but in this case you'll notice that there's a double bond in each, which kinks the chain and makes the fat molecules not packed together so well, so they tend to be liquids at room temperature. Collectively, we refer to all these types of molecules as triglycerides or triacylglycerides. This is because they're essentially a glycerin molecule, which has 3 alcohol groups, condensed with some type of carboxylic acid or fatty acid. And these molecules are very easy to come by because they can be taken from natural sources. And it turns out that when we hydrolyze them, we get very useful products. Shown here are just a few of those products that can be taken from the hydrolysis of esters like triacylglycerides. You may notice the names of some of them, such as lauric acid and stearic acid, which you'll frequently see in soap products. So let's think about how we get these using a saponification reaction. The saponification of any of the fats or oils, remember those triacylglycerides I showed you 2 slides ago, should lead to the formation of a glycerin molecule and 3 fatty acid salts. It's those fatty acid salts that the soap makers are after. Once you collect those and separate them from the glycerin, a simple pH adjustment can give you the organic acid, or naturally you could leave it as it is and use it as the fatty acid salt. And it's the saponification of the fat or oil that leads to those useful products. As a means of demonstration, here is a modern soap product that the manufacturer would like to have you think is made from some of the most carefully crafted, scientifically created and formulated ingredients. But if we look closely at the list of ingredients in this product, most of them are taken simply from the hydrolysis of fats, in this case mostly coconut oil. There are even more ingredients here that are simply taken naturally from vegetable products and combined. In fact, you'll find very few ingredients in modern soap products that aren't naturally sourced in this way. But the history of saponification goes much farther back than recent history. In fact, this may have been one of the very first chemical reactions harnessed by modern man to make a useful product. And in this guest lecture, Professor Tyler Durden was going to explain to us his theory on how this process was first discovered. So, let's take a listen to Professor Durden's thoughts and then evaluate them once we're done. So exactly what is it that Professor Durden was up to? Well, his explanation of what he was doing is actually quite accurate, with the exception that it was done out of order. This is because Professor Durden needs to end on the chemical lye so that he can continue his story. In truth, lye is one of the early ingredients in the process. You see, tallows basically refers to fats. Now, Professor Durden's source of fat is sort of a grisly one, so I'm going to show you a picture of a different source of the fat. Nonetheless, it's animal product. Once that fat has been isolated from the remainder of the animal, he uses lye, which is just potassium hydroxide, easily obtained at any hardware store. He uses the lye to hydrolyze the tallows into two things, a carboxylate salt and glycerin. He's making soap and also the ingredient that goes into many hand creams. But Professor Durden has a much more diabolical plan than simply selling hand cream. What Professor Durden does is he sells that soap that he creates and gets money, which he uses to purchase nitric acid from a chemical supplier. That nitric acid is then recombined with the glycerin byproduct to form nitroglycerin, something that we will not be making in lab this week. But Professor Durden's explanation is in fact quite possible and very plausible. If someone were to have the intention of creating a bomb-building empire underground, this may very well be the way that it would be done. Our goals in lab this week are much less diabolical than Professor Durden's. We are simply out to demonstrate that we can use esterification and hydrolysis interchangeably in the lab depending upon the goal of our particular synthesis or experiment. And we're going to do this by combining an acid and alcohol to form an ester in a nearly quantitative yield, and then deconstruct that ester back into the corresponding alcohol and acid using a saponification. In each case, we'll measure our yields and confirm our synthetic success as a demonstration of the principle that reactions don't necessarily have to be unidirectional. Sometimes we can use them in whichever direction suits our needs. In order to accomplish this, we'll be working to first create an ester from benzoic acid and methanol. The ester that we'll make is called methyl benzoate and smells a bit like peppermint or flowers. Once we create that, we're going to demonstrate that the product is free from the original solvent methanol and the byproduct water by characterizing it using IR and NMR spectroscopy. Next, we'll take that product and hydrolyze it back into benzoic acid and methanol. And again, we'll prove that the product we've created is completely free from solvent and byproduct and characterize it using IR and NMR spectroscopy. At the end of this, we'll assess exactly how much yield we were able to achieve in each of the two reactions, thereby hopefully demonstrating that we can use the reaction in either direction. So this week in pairs, you'll be preparing methyl benzoate from benzoic acid and methanol. You'll then analyze that product by IR and NMR spectroscopy to determine purity and identity, and you'll get a yield. You'll then immediately hydrolyze your product back to benzoic acid and methanol using a saponification reaction. And again, you'll isolate your product, analyzing it by IR and NMR spectroscopy to determine its purity and identity. You'll then weigh it to determine the yield of that reaction as well, and we'll clean up the lab. And then we'll be off to write a paper explaining how and why we were able to create methyl benzoate from benzoic acid and then benzoic acid from methyl benzoate by carefully constructing and choosing our reagents in the lab.